All right, so last time we were working with Bootstrap distributions, using them to approximate the value of population parameters. So I want to pick up with where we left things off, which was kind of working, we were right about here on worksheet 12, part 1. And we were constructing Bootstrap confidence intervals. So we'll pick up from this spot here. I just want to let you guys make sure that you know you've got homework assignment is due Wednesday evening. I am not going to give you guys a quiz on Wednesday. You guys can just focus on finishing up your homework. We have our second exam is a week from today. So on Monday, we have exam 2 of next week. So for class on Wednesday, we're just going to review for the exam that's coming up next week. So that's the plan for this week. So before we get going, there are 2 R Markdown files that go along with these worksheets. So if you actually want to write the code, make sure things are compiling correctly, I'm going to be doing my work in those R Markdown files. So you might want to have those open in addition to these PDFs. But any questions before we get started today?
About the exam, will the exam cover chapter 6, or is it just going to be up to 5?
Yeah, so the original plan was to have some material from chapter 6 on it. Because we have this snow day, it's just going to be on chapters 1 through 5.
Cool, thank you so
chapter
much.
6 will be on the next exam.
Cool.
Anything else? Okay, so I am going to open up R Markdown or R. So this over here, what I'm working with is this file that is called Bootstrap Part 1 R Markdown. And maybe if you guys have a preference, do you prefer that I kind of mark up a PDF or that I work in the R Markdown, or you don't care?
I'm fine with either.
The R Markdown.
Okay. Okay, so just to catch up, last time we did work with 2 examples. One of them was the birth weights for working with North Carolina births 2004, and we constructed a confidence interval for that, or at least a bootstrap distribution for that, and we did it for the arsenic data. I just want to start with this one. So question 8, I believe we did this last time. I just want to make sure it's clear. So the idea here is there's this data set, Bangladesh, which has 271 observations in that data set from groundwater samples. And one of the variables they tracked was what was the arsenic level in the sample of water. And so if we want to, say, come up with an estimate, so the question where we might want to use this, we might just ask, like, what is the mean arsenic level in groundwater in Bangladesh? And we collect 1 sample, right? And we want to answer this question based on the 1 sample that we collect. So initially, let me load this. We could just run some of this code over here, and I didn't put the output on this. And we can just take a look at what are the sample mean and the sample standard deviation. And we say, okay, the mean arsenic level is 125 parts per billion. That's probably the best guess that we would have for the average arsenic level in Bangladesh. But again, right, we want to build in some margin of error due to the variability of sampling. And that's where the bootstrapping comes in. Was there a question? Okay, so certainly we can construct a histogram if we wanted to answer some of these questions. I don't remember if we did this last time, but some things that you could plot here is we could plot histogram of arsenic. And then we could run some of these codes over here to kind of see how normal looking our data might be. And what we see from this is that, right, our data is not normally distributed at all. We have data which is very heavily skewed. But we can still do this process no matter what our sample looks like. So it doesn't need to be normal is the point here. Okay, so then what we're going to do now is set up a bootstrapping process when we have just one sample, and then we'll take a look at what happens when we're comparing two different groups next. So if I just have one sample, I can use this length argument. This is going to count how many observations were in this vector arsenic that we created. We're going to create 10,000 bootstrap samples, and we're going to store the means of each of those in this thing called boot mean. And again, you can call these things whatever you like. So now we're going to set up our loop. So what I'm going to do is randomly sample my bootstrap sample, right? Should have the same number of things that were in the original sample. So we started with n things in the original sample. So n, again, is this value over here. It's like 271, something like that. And I'm going to pick exactly the same number of things for my bootstrap resample. So the bootstrap resamples should have the same number of observations as the original sample. And with bootstrapping, spell that correctly, we do put each value back in. So we do replace, or else we're going to just get back the same sample that we started with. So we're going to sample with replacement. That would look like this. And since we're trying to approximate the mean arsenic level, that's why we have a mean over here. So any questions about the bootstrapping?
I just had a question. On one of the homework problems, I kind of used this section of the notes. So why here are we using just the sample instead of like the R norm or like the different type of sampling?
Because we want every value of the original sample to have an equal likely chance of being picked. So this command sample means out of all of the integers from 1 up to n, pick n of them, replacing it each time. So we're not picking from a normal distribution. We're not picking randomly from any sort of distribution. When we're bootstrapping here, we're picking values from our original sample. And we want each of those values to have the same chance of being picked.
Okay.
So we're not picking from like a theoretical distribution. We're resampling from the original sample that we started with. Okay, and so then these all were stored in, not in this thing called result, but in this problem, I called it boot mean. So we just make sure we kind of have things named consistently. And I am going to put a vertical line. What did I call this? Sample mean. At sample mean. Okay. And so this is going to just put a mark at like the mean that I got from my sample. And so let's see what this does. That was pretty quick. That seems weird. why is my sample mean so far over here? Oh, let's see. You guys getting something similar? I feel like my center should be, maybe it's okay. Maybe it's because, I think it's okay. I think it's just because our data is so skewed to begin with, might be part of this problem here. Are you guys running this and getting like similar looking code, similar looking output? I hope you're running it. Here it is in the solutions. No, this one looks okay. That's what we should be getting, things that are a bit closer to the middle. Oh, I know what I did wrong. I'm randomly picking numbers here, right? So sometimes when I make these mistakes, I do them correctly. This is becoming a common theme here, right? I'm making lots of mistakes on purpose. Let me just like keep track. So how the bootstrapping works is you have your original bootstrap, you have your original sample, and then we're going to pick a value from that sample and then put it back in, right? And then we're going to pick another value from that sample and put it back in. We're going to do this until I have the same number of things that were in the original sample. Does anyone see what's wrong with this line of code that I have here? This is where I messed up.
You have sample n out of n.
Yeah, so one of these n's should not be an n.
The first one should be arsenic, right?
Yeah, that's right. Sorry. Right. So what we're doing is we're picking values from the original sample. Right. So we're going to pick n values from arsenic with replacement. Sorry about that. It is good to kind of run through, right? You should expect your observed sample to be close to the middle of your sampling of your bootstrap distribution. So when you see things like I just saw, you should be a little suspicious. It might be because the sample was skewed, but these should be pretty close to the middle. So this looks a little more reasonable to get for a bootstrap distribution. Just be sure that, yes, we're picking values out from the original sample, in this case, which was arsenic. For this, we could certainly do a QQ plot. And here our bootstrap distribution was called boot mean. Just to get a sense of how normal or unnormal this is. We can see that it's not too normal, right? We're kind of having more stuff in the tails than we would expect with the normal distribution. Any questions about that so far? Okay, and so then last time we talked about two different ways that we could construct what's called the 95% confidence interval. So one, we could do kind of like an informal approximation by saying, if I go 2 standard errors above this mean and below this mean, so maybe I go, 1 standard error, 2 standard errors this way, 1, 2 standard errors this way, then I can get a region that has about 95% of the sample, bootstrap samples in between. And that's what excuse me. So that's what this was doing. So this is saying go 2 standard errors above the sample mean, go 2 standard errors below the sample mean. And that's one way to get a 95% confidence interval. When things are not normal, like we have in our distribution, you want to get a better estimate by using the quantile function. So this is going to go in and find the value that cuts off the bottom 2.5%, that cuts off the top 2.5%, and everything in between these two would be the middle 95%. So this one gives us slightly different values than the one that we had up top. So this would give us a better estimate for that 95% confidence interval. So that's the arsenic example here. And if we wanted to interpret what this means, which we definitely want to do, again, this interval is giving a range of plausible values. Right, so it's giving us a range of plausible values for the mean arsenic level for the population of all groundwater in Bangladesh. So oftentimes we would state this by saying we want to attach some meaning to what the 95% is saying. So there is a 95% chance that the interval So that's how we could try and make sense out of those values that we just found. So the 92 to the 163 is giving us an interval that has a 95% chance of capturing the actual population parameter we're trying to estimate. And this is better than saying, I'm just going to estimate it with one value, which is the sample mean that I have. Okay, any questions? So, okay, so that catches up to where we were last time. And we did a similar thing with the births last time, where we constructed sampling distribution, bootstrap distribution for them. And I called all of that work I stored in this thing called result. And so if I want to construct 95% confidence interval for the mean birth weight, which is over here, so for this case, we stored our bootstrap means in a vector called result. So first of all, I want to run some R. So if I want to find a 95% confidence interval, up here, then I'm going to run quantile function on result. And again, the reason why I chose result is because this is where we stored those bootstrap resamples for the birth weights. And we can enter both of those cutoffs in the same command like that. And so here we could think about this as saying, well, there's a 95% chance that the interval from here, I just put inline R code that was holding the spot of that result, but is going to go from here up to here. And if you're running this code, I hope that you're not getting the same exact values, but things that are pretty close to it. So here we could just say, right, there's 95% chance the interval from 3,418 to 3,478 grams contains the actual mean birth weight in North Carolina. Any questions? What do you think would happen if instead of saying find the 95% confidence interval, we wanted to find that 90% bootstrap confidence interval? What do you think we need to tweak?
We'd have to change the values, and that the 0.025 and the 0.975, those would have to be 0.5 and 0.95.
Yep, that's right. So that means we would want to exclude the bottom 5% and the top 5%, right? So that means we're excluding 10%. We want the middle 90%. So that means we rule out the bottom 5 and the bottom and the top 5%. So that's where these come from. That's right. So we don't need to kind of change how we're bootstrapping. We just change the cutoffs. And really what's important to note here is what happened when I decreased the sample size.
Shouldn't the interval shrink?
So we could see, so here was the 95% confidence interval, and here was the 90% confidence interval. So what happened when we changed the confidence level, we made the confidence level smaller, we decreased it from 95 to 90%, then the interval estimate, what happened to it?
It got smaller?
The interval got smaller, right? It got more narrow. That's right. So when we decrease the confidence level, our interval estimate becomes more specific, right? It's less wide. Okay, and hopefully this makes sense since the more narrow our interval is, the less likely it's going to be to contain the population parameter. So I can give like 100% confidence interval for things by saying it is somewhere between negative infinity and positive infinity. And I know I have a 100% chance of being right about that. But sometimes when we make our estimates so wide, we really don't get too much information about that. So there is some trade-off between how successful do we want to be versus how specific do we want the estimate to be. Okay. Good. So let's see where we are. If you're following along on the worksheet, we just took a look at question 11. Okay, so now we're going to think about looking at comparing two different populations. So here, this data set in this table is comparing the length of commercial times on basic cable compared to extended cable. And so they took like a half-hour period of time, and they looked at, out of that half hour, how much of that time was commercials being played. And so looking at the data here, we can see these were the values for basic cable, and these were for extended cable. And I imagine like extended cable means you get some of the premium channels and all of that stuff. Guess people don't use cable too much these days anyway. And what we want to consider is, you know, is there a difference between the amount, the commercial times on basic cable compared to extended cable? So here, this data set is not in resample data, but I did enter it in for you, so you don't have to enter it in. And notice that this is not a matched pair situation, right? There's no natural way of comparing this 7 minutes of commercial with this 3.4 minutes of commercial. If they were somehow, you know, matched, that we did this at a certain specific time or whatever, but based on how this data was collected, there's no natural way of pairing values in one data set compared to values in our other sample. And in particular, we have different sample sizes. So when you have different sample sizes, that's a pretty good indication that there's not going to be a natural way to match these up. So these are our two different samples. And if we want to kind of do some exploratory data analysis, I just put in some different ways that we can compare these two. So, you know, before you even get going, you might not even know what statistical questions are worth asking. And that's where exploratory data analysis comes in. And if you're kind of curious about this, there's a class 3376, which is called Data Visualization and Wrangling. And that is basically a class on exploratory data analysis. So you'll get all into those details. But if I'm looking at this plot, for example, yeah, it seems like that's pretty compelling evidence that basic cable seems to have more commercials than extended cable does, right? This box is above this box. And the question is, are these differences big or not? And we don't necessarily know what is a big difference until we see it kind of the bigger picture. How does this relate to differences that we observe in other Bootstrap resamples? So when we go through this process, we're gonna go about this differently. Since this data is different, we've got two different samples here. So I'm gonna still bootstrap 10,000 of these samples. And now I'm going to choose to store them in this vector that I'm calling times difference in means. And really what we're trying to estimate here, what I would use this interval to estimate is maybe I could say it like this. What is the difference So we could use confidence interval to estimate that. And again, here, the difference between this and what we were doing with hypothesis tests is there's no claim here, right? I'm not claiming basic has longer commercials than extended. We're just trying to say, I don't know anything about these values. Let's just get an estimate for them. So when we do this bootstrapping, let me just pick off this piece of code that I want up here. Here we are. So what we're going to do is bootstrap for each of these two samples separately. So I'm going to have two of them. So I'm going to have like a bootstrap for basic and a bootstrap for extended. And just to recall, these samples we hand entered in. So one was called time basic times extended. So for this basic bootstrap resample, we are going to pick from this vector over here. So we're going to randomly select values out of this one with replacement. And how many values are we going to pick out of this vector of values?
Ten.
Yeah. Why 10?
That's how many elements in that set.
Yep. So we're going to pick out of this sample of values, we're going to pick 10 values. Each time I pick a value, I put it back in. And let me just kind of and if you're kind of curious what these things look like, you can always check one line of your code and say, okay, so that's one possible bootstrap resample that we got by picking 10 values with replacement from up here, right? So the 8.5 got picked, the 8.6 got picked, and so on. And then we do the same for the other sample. So we're going to create two different bootstrap resamples, one for basic cable, one for extended cable. And for the extended cable, we're going to pick 12, right? Because that sample size had 12 values in it. So it's going to pick with replacement from the first sample. It's going to pick with replacement from the second sample. And then these are going to be like our placeholders for resamples for basic and for extended. We calculate the mean of each of these, and then we take the difference, we store it, and then we go on again. So down here, that's what these two lines are doing, right? So this is our resample for basic. That's our resample for extended. And then we're going to calculate the difference in these means. And we're going to do that 10,000 times, right? So this will store all of those things in this thing that we're calling times difference mean. So let me replace that over here, since that's what we call this thing over here. Any questions about how we set up that loop? These are going to just calculate the mean and the standard error of the Bootstrap distribution. And then if we want to find these cutoffs, I'll do them separately. For the lower cutoff, we're going to take the quantile of what data set. So it's going to be my first entry into this quantile command for this problem. You guys can chat it if you prefer not to. Yeah, so the 0.05, that comes over here. That's right. So we're going to find the 0.05 quantile of what data set?
The one that we manually entered in those vectors.
You mean up here?
Yeah.
So we're finding cutoffs not from the samples, right, but from the Bootstrap distribution. So we're finding like what are the middle 95% of the Bootstrap resamples statistics.
You know, times.diff.mean.
Yeah, so we want to find the cutoffs of the Bootstrap resampling distribution. That here we call this times.diff.mean. And because it's 90% here, that's right, we cut off the bottom 5% and we cut off the top 5%. Sorry, I just asked questions because I just want to make sure everybody's along. Since I can't see most of you, it's all I got. It's a chat. That's all I'm left with at this point. So please, you all are certainly encouraged to ask away or answer away. But this is going to give me the middle 90% of Bootstrap resamples, right? The differences in these two means. And now I can come down and plot all of this. I will plot the observed. So the observed difference we calculated and we called observed. And then let me add lines at the lower and upper cutoff.
Are you declaring the variables in the console so the code chunk can access it, even if they're in a different code chunk?
It still reads them in. It should still read those values in that they were stored from a previous chunk.
Because mine is like, when I try to run a chunk, it's saying it can't find whatever the variable is unless I declare it in that chunk.
So I'm going to run it over here. And now those things aren't defined over here. They should still work over here. So you might just need to run this code chunk first, but they don't need to be in the same chunk.
Okay, as long as the first one is run, then it'll be recognized.
Yes, it just needs to create those things that you're assigning values to. Yeah.
Okay.
Yeah, so mine are in different ones, but I did run this one first before I ran the other one. Yeah, and that worked. Okay, so let's see. Let's run this one. Yeah, so here you can see kind of the observed difference was like this slightly over 2-minute difference that we have. And here we're getting the middle 90% of the samples are somewhere between about 1-ish and about 3.5. And it didn't print those out. So what I'm looking at, these values over here, this value is the mean of the Bootstrap distribution. This value over here is the Bootstrap estimate for the standard error. Let me just output these values. I could do inline R, but that's okay. So here we can see these were the cutoffs that match what we had in this figure over here. So one of them is about 1, one of them is about 3.5. So these interpretations kind of take on a fill in the blank type of thing. We don't need to kind of reimagine how we interpret these things. We just need to kind of frame the interpretation in whatever context we're in. So first of all, here, this was a 90% confidence interval. So this is going to give me a 90% chance that the interval from 1.17 minutes to 3.42, I'll round that off, minutes, contains the actual value for the mean say something like that. So we just want to kind of say what it is that we're estimating. So in this case, we're trying to estimate the difference in two means. So we can kind of extend this out to from our sample to all times for basic and extended. Any questions? And ultimately, when we're doing hypothesis tests, we might say something like this. Right. Is there a difference in the amount of commercials on basic and extended cable? And if this were the case, then the alternative hypothesis would be there is no difference. And the alternative would be there is a difference. And based on what we found up here, which of these claims do you think is more likely to be true?
Wouldn't the null hypothesis be more likely to be true because it's more likely to be in the interval that we have?
So if there is no difference in these two, then we could state it like this, that the basic cable minus extended cable would equal what?
0.
Yeah.
Oh,
And
just what it is, not. Okay.
yeah.
Sorry.
So I'm going to try and state this. Maybe that'll help answer the original one. So here we would say that this one is going to be not equal to 0. So this just gave us, this being up here, this is where the actual difference in the means is going to be, right? These are the plausible range of values for these differences. Does 0 fall in that range?
No, sorry, I cannot read. It would be the alternate hypothesis be more likely to be true?
That's right. So from this over here, we can see that 0 is not inside that confidence interval. Here we're seeing that 0 is not a plausible value for the difference. Okay, and so this tells us that there is a difference. And so on your homework, you guys are asked to kind of, in some cases, interpret your confidence interval in terms of like, does this confidence interval seem to indicate that some treatment has any effect, or is this group actually any different than the other group in some way? And so really what we're looking for in those cases is if 0 is in your confidence interval, then that gives you evidence that there might not be any difference between these two. If 0 is not inside your interval, then that gives you good evidence that in fact this difference is not 0 and this group is different from that group. So that's kind of what you're honing in on when you're doing a confidence interval for a comparison of two groups. What you're really interested in is 0 inside my confidence interval or not? Okay, are there any questions? Okay, so then we're gonna jump into Bootstrap part 2 of this. So I'm in a different R Markdown file. This is the other PDF, part 2 of Bootstrap resampling. And so I just want to kind of talk about a couple of other types of bootstrapping that we might do. And so we could do bootstrapping when we have matched pairs, such as this one over here. This is this wetsuit problem. And this is what you guys did some reading about for the quiz today. And so when we're bootstrapping for matched pairs, we're not going to be picking like one bootstrap out of all of these and one bootstrap out of all of these and then taking them differently, because again, that kind of ignores the matching that we have in this data. So instead, what we're going to do is create a vector of differences, and then we're going to pick bootstrap resamples of that difference. So for example, we have these vectors, wetsuit, no wetsuit. So I need to run this because it needs to know what diff is. So down here we can see, right, this would be like the corresponding bottom row of a table where this is calculating the differences in each of those pairs of maximum values. So now when I do a Bootstrap resample here, we're going to sample out of those differences. And we're going to pick the same number of things that were in the original sample. Our original sample had 12. And we are going to replace each time. So up top here is the original sample, and down below is one possible Bootstrap resample that we would get from that. So actually, when we're doing matched pairs, it's actually closer to what we did when we were just bootstrapping for one statistic, right? This is closer to what we did when we were trying to estimate like the mean arsenic level or something like that. Here we're trying to estimate the mean of the differences of pairs. Okay, so yeah, so writing out two possible Bootstrap distributions, I could just write code that's going to generate two possible Bootstrap distributions. You can see, right, each time we do this, we get a different sample that still consists of differences from our original vector of differences. Okay, questions about how that bootstrapping is working? Okay, so if we want to bootstrap this, I'm just going to copy a bunch of this stuff. So here was the first example we did with the weights. Okay. Did I set this up a little bit? I did. Okay, good. So we've got like a blueprint for this. That worked better. So right over here, this length diff is going to calculate how many matched pairs we have. Just note this should give us 12. We could do 10 to the 5th. Usually we do 10 to the 4th. You can pick whatever you want over there. I'm going to save this in a vector called boot difference. And so now when I'm picking my samples, and you'll have some questions on your exam like this, fill in the blank. What goes in the first blank in the sample formula here?
The sample you're choosing from?
Yeah, that's right. Thank you. And Max got that in. So that is diff in this case. That's right. So we're not picking from the wetsuit. We're not picking from the non-wetsuit group. We're first taking the differences of each of those pairs, saving that to a vector of differences, and that's what we're sampling from. And so how many are we going to pick from difference?
Whatever the length of difference is.
Yeah. So yeah, we could put 12. We can put n there as well. That's right, since we created that number. And with bootstrapping, replace is going to be
True.
true. Yep. So keep that in mind. Whenever we're bootstrapping, we are going to replace true. So I pick this sample, and then what is the statistic that I'm now going to calculate for each of those bootstrap samples?
You just want the mean of the result.
Yep. Yeah. And so here we need to be careful, right? This should be called boot diff. And then this is going to be the mean of that. And again, what you call these things, that's up to you. So this is going to create all of that bootstrapping. Then when we create these quantiles, we're now going to go into our bootstrap distribution, which I call boot diff. And then we calculating, in this case, 95% confidence interval means we have, we cut off the upper and bottom 2.5%. And then all of this is just gonna create the histogram, put in our observed value, put in the vertical lines where our cutoffs are, and this is gonna calculate the mean of our bootstrap distribution and the standard error, the bootstrap estimate for the standard error of the sampling distribution. Something crapped out for me. Oh no, what did I do here? This is like a temporary thing, so I can call this whatever I want. Sorry. What I'm storing is the mean of that. Okay, right. So that's kind of like a temporary thing. We pick a sample, and then we calculate the mean of that sample, and then we want to recreate that sample. So it doesn't matter what we call that thing. And here's my bootstrap. That seems reasonable. And these are the cutoffs that I'm getting. So hopefully you're generating something pretty close to those values. So to kind of summarize what this is saying, this interval is from 0.605 So what we can see here is that the interval from like 0.07 to 0.09 meters per second. So these were measuring maximum velocities. So this interval contains the actual difference in maximum velocities. Again, because 0 is not inside this interval, this would also give us evidence that would say that it really isn't plausible to say that this wetsuit isn't making a difference. If that were the case, we would see that 0 is inside this interval. So we are getting a confidence interval that only has positive values. So that's a good indication that the wetsuit is actually making people, or at least has the effect of people are swimming faster than they did without the wetsuit. Any questions about how that worked with matched pairs? So keep in mind, so far we've done bootstrap distribution for a single sample, for a single sample statistic, like the mean birth weight, the mean arsenic level. And then we've done different comparisons. We've done one where we've compared two independent samples, like the cable times. And we've done one where we've looked at matched pair samples, like the wetsuit example. And all three of these are similar, but we need to tweak them a little bit based on the context. Okay, so let's try one more example, and then we can kind of just summarize this process. So here is this example on that worksheet that deals with repair time. So this is in the data set library resample data. I should run that if I haven't already. And And so that data set is called Verizon. And so not to get too bogged down in like repair times for wireless providers or cell phone providers, but what this is comparing is like when you know, a cell tower goes down, there are smaller companies that don't put up their own cell towers, right? They use towers that Verizon uses for their own cell network. And so the question is, does Verizon respond faster to fixing things for their own customers as opposed to they also maintain, excuse me, infrastructure for other companies? So like if some customer for some other company is complaining that some Verizon tower is down, so I can't use my other cell phone service, do they respond just as quickly as if it was their own customer that was calling them? How we can break this down is the ILEC. This is when they make repairs to for other local customers. So the CLECs, these would be for customers for other competing local things. So ILEC is like repair time for Verizon's own customers. The CLEC would be, these are the repair times when they are repairing infrastructure for other companies. And so we could compare the difference in the means of these two companies. Another thing that we might want to compare would be like the ratio of the mean repair times. And we might want to see how close is that ratio to 1, right? If the ratio of the repair times was 1, that means it takes the same amount of time to repair their customers as other companies' customers. So the first thing that we need to do is just subset this data. So this is a data set that has all of these things jumbled up together. So here we're going to go into the Verizon data set. And what we are interested is thinking about repair times. We want to compare repair times. So we're going to select time. That's the variable. And so for the first data set, this is going to be the ones where we're going to want to just take all of the observations of the ILEC group. So here, this group would be ILEC. And we need to put that inside of double quotes, and this one would be the CLEC. And then we do the drop T because we just want these things to be vectors. So this is going to create 2 vectors. One vector is going to be all 1,664 repair times that they made for their own customers. The other data set is going to be much, much smaller. It's just going to contain 23 values for this one. Okay, so now we come down here, and this is, since we don't have matched pairs, these samples are different sized. We're gonna just pick 2 Bootstrap samples separately. We're gonna do the same approach that we did with the cable commercial times. So I'm gonna go into sample time ILEC, and how many values am I gonna pick from that vector?
$1664.
Yep, we're going to pick the same number of observations that were in the data set, the original sample. Yeah, thank you. So that's going to be the 1,664. And that means for this one, we're going to pick 23 values there, right? So we're just kind of randomly selecting within these 2 things separately, distinctly. And with bootstrapping, we pick with replacement. And now we want to calculate the ratio of the means. So in other words, I'm going to take the mean of the, and capitalization does matter here. We're going to take the mean of this Bootstrap resample of the ILEC times, and then we're going to divide that by, so I just put this, division symbol here, the mean of the CLEC sample. And I think that should do the trick for us. So in this case, we needed to change the statistic that we're calculating each time. In this case, we wanted to consider the mean repair times, the ratio of the mean repair times, excuse me. So we're going to go into our Bootstrap distribution, which is called time ratio mean, and we're going to pick off the bottom 2.5 and the upper times here. So any questions about this before I run the code to see what happens? So that's what I'm getting for my 95% confidence interval. So hope you're getting something close to those. Any questions? So when you're kind of working on these homework problems, there's a couple things you want to keep in mind. And first of all is, does this question require me to do a permutation distribution, or should I be doing a Bootstrap distribution? And that depends on whether you're doing a hypothesis test, you always use permutation distributions, or whether you're doing a confidence interval. So whether you're doing permutation distributions or bootstrapping depends on whether there's a claim being made about the population parameter or not. So I think as you're thinking about these, you might want to think about, am I doing permutation distributions or bootstrapping? And once you kind of figure that out, then think about, is this one sample? Is it matched pairs? Is it two different samples? And that's going to affect the type of code that you would want to use to create those distributions. And here's what this one looks like. And this is what's really nice. There is no central limit theorem for the ratio of two means. There's no way that we can theoretically describe what this distribution looks like, which we could do for means and differences of means and proportions. So for cases like this, there are many statistics that we don't have a central limit for. So we can't do it theoretically. So all we can do it is experimentally by bootstrapping. So it's really powerful. We can bootstrap anything. We can't use the central limit theorem for anything. So this actually has more universal application than, say, the central limit theorem does. And so the last thing that I want to talk about, well, I'll stop here for today and we'll tie up this loose end next time. So you might have a couple of problems in homework that get at this question of bias, and is there too much bias in the problem in order for this to be an accurate estimator? And so that's a small piece. I just want to fill in that last little piece of it next time rather than try and do it in a couple of minutes right now. But what these two lines are representing, the blue line is the original ratio that we had. That was like about 0.5. And the red line is the center of our bootstrap distribution. And what we can see is that these two values are not the same. And this difference in these two values is what we call the bias of this estimator. But that's what we'll talk about next time. Okay, so I will stop here. If you have any questions about the work that you guys are doing for Wednesday, happy to answer some questions if you want to stick around. Otherwise, I've got office hours tomorrow. And I'll get up some materials for the exam. And again, the plan next time is to just kind of tie up this loose end about estimator bias, and then we'll just talk about the exam. Okay, well, thanks everyone. Have a nice afternoon, and I'll see you on Wednesday.